For centuries, the wind has moved our world. Today, the modern wind turbine captures that invisible kinetic energy, turning it into the stable electricity that powers our cities. This process is a marvel of engineering, balancing aerodynamic forces with complex electrical demands. Its core function is the precise conversion of airflow physics. The entire machine is designed to perform one continuous task: absorb the wind's power, transfer it, and stabilize the electrical output for the national grid. First, let's understand how the enormous blades capture kinetic energy, converting the simple movement of air into powerful rotational force. The blade is not a simple paddle. It is an aerofoil, designed exactly like an airplane wing. It utilizes pressure differences to generate lift, not just simple push. The wind passing over the curved side travels faster, dropping the pressure. This pressure difference creates a powerful lift force perpendicular to the wind flow, driving the rotation. To maximize this lift, the blade is carefully twisted from the root to the tip. This unique design accounts for the different wind speeds experienced. Along the blade's length, the goal is to maintain the optimum angle. For the relative wind speed, a complex calculation that ensures maximum energy absorption from the airflow. Once the airflow is successfully converted to rotation, that slow, powerful turning needs to be conditioned for electricity generation. The giant blades typically rotate at a very low speed, perhaps only 10 to 20 revolutions per minute. This is too slow for any meaningful power generation. To achieve the high speed required by the generator, the rotation is routed through a powerful gearbox. The workhorse of the nacelle, the gearbox uses a series of precision planetary gears to step up the slow blade rotation by up to 100 times, preparing it for the generator. This increased speed is now coupled to the generator. This machine uses the principle of electromagnetic induction to convert high-speed mechanical rotation into raw electricity. However, this raw electrical output is often unusable. Because the wind speed is constantly changing, the generator's output frequency is also constantly fluctuating. Before this power can even be considered for the grid, it must be perfectly regulated and stabilized. This is the task of the power electronics. The conversion unit first turns the variable AC into stable DC, a process called rectification, and then converts it back into perfectly clean, fixed frequency AC. The turbine must always face the wind. A velocity sensor and a wind vane on top of the nacelle constantly monitor the speed and direction of the incoming airflow. Any deviation from the optimal direction is quickly corrected by the yaw system, which slowly rotates the entire nacelle to align with the wind. This yawing motion is crucial for maximum power extraction and reducing lateral stress on the tower, ensuring the turbine always presents its face to the wind. Equally vital as pitch control, this mechanism adjusts the angle of the blades themselves to optimize performance for the current wind speed. In high winds, the blades pitch out of the wind's path, catching less air. This prevents overspeeding and mechanical stress, protecting the entire system from collapse. Conversely, in light winds, the blades can be pitched to maximize surface area and capture every available pocket of kinetic energy, ensuring power generation continues. For emergency situations, a brake system is in place. If the electronic controls fail, this hydraulic brake instantly clamps the high-speed shaft. This instantaneous stop is necessary to prevent catastrophic damage from extreme winds, protecting both the massive machinery and the surrounding environment. To keep all these systems yaw and brake functioning flawlessly, a sophisticated electronic controller sits within the nacelle, acting as the machine's brain. This controller continuously processes data on wind speed, temperature, and generator output, issuing commands dozens of times per second. The entire nacelle, the gearbox, generator, and controller must be properly cooled. A powerful HVAC system prevents sensitive electronics from overheating. And finally, for maintenance, a small elevator or ladder allows technicians to climb the 300-foot tower to access the nacelle for routine service and repairs. The stabilized, fixed-frequency power now begins its journey down the tower. It must first be stepped up to handle the transmission distance. At the base of the tower or nearby, a step-up transformer increases the voltage significantly, preparing the electricity for the high-voltage collector lines. The power is then routed through a collection network, joining the output of every other turbine on the wind farm. This large volume of synchronized power travels to a central substation. Here, further voltage regulation and monitoring ensure quality control. Crucially, the power is synchronized with the utility grid's own power. This ensures seamless integration, preventing any destabilization of the national energy supply. From the substation, the power is fed into the national transmission system, traveling hundreds of miles across the country via high-voltage power lines. Finally, at the consumer level, distribution transformers lower the voltage for the last time, making the power safe for homes and local businesses. This final stage completes the conversion cycle, from the chaotic energy of the wind, through complex machinery and electronics, to stable, usable power in your wall socket. This reliance on fixed-frequency AC power demonstrates the fundamental truth. Modern wind power is as much about the electronics in the nacelle as the aerodynamics of the blades. The turbine is not merely a windmill, it is a highly sophisticated, self-regulating power plant, converting air into a commodity. But how efficient is this process? The science of aerodynamics places a physical, unavoidable limit on how much energy any turbine can extract. Imagine measuring the wind speed before and after it passes through the blades. The speed must be slower downstream because energy was absorbed. If the turbine were 100% efficient, it would stop the wind completely, making the downstream wind speed zero. But this is physically impossible. This physical reality leads to Betz's limit, a principle stating that no turbine can convert more than 59.3% of the kinetic energy available in the wind. Modern large turbines operate with a highly efficient design, often reaching mechanical efficiencies of around 45% to 50%, close to the theoretical maximum. This high efficiency confirms that the meticulous design of the twisted aerofoil blade is working exactly as the laws of physics intended beyond the mechanics. The choice of generator is evolving. Many modern turbines now utilize direct drive generators. By eliminating the gearbox, engineers remove a frequent point of failure and simplify maintenance, despite the resulting need for a much larger, heavier generator unit. This evolution reduces reliance on lubricants, cooling systems, and heavy maintenance work done hundreds of feet in the air. The mechanical durability of the entire tower is constantly monitored by numerous sensors for vibrations and stress, ensuring structural integrity in all weather. Extreme weather like lightning is mitigated by lightning protection systems, which safely route massive electrical strikes down the tower and into the ground. The modern wind turbine also requires sophisticated cybersecurity to prevent unauthorized access to its electronic controllers and critical grid connections. The future of wind power is moving offshore. Offshore turbines are significantly larger, capturing stronger, more consistent winds over the ocean. These immense structures can reach over 800 feet tall, generating power far more reliably than their onshore counterparts, directly feeding coastal populations. In conclusion, the wind turbine is a masterpiece of interdisciplinary engineering, perfectly fusing aerodynamics, mechanical power, and power electronics. It is the essential link between the raw, chaotic energy of the atmosphere and the precise, stable demands of the electrical grid. Every component, from the twisted blade to the electronic converter, plays a critical role in achieving this fundamental transformation. The reliance on fixed-frequency AC power ensures that the clean energy generated high in the air is instantly usable in your home. It represents the very best of green energy innovation, transforming a natural force into a core building block of our sustainable future. If you were impressed by this complex mechanical and electrical fusion, let us know in the comments. Like, share, and subscribe to UA Electric for more deep dives into the technologies that power our modern world.